we'll actually start recording, sort of. Do you guys have any questions from last week? How many of you actually looked at the homework? The rest of you should probably look at the homework. It is really, really long right now, and as long as it may seem, I cut it in half from what Sapling originally put up there. Okay, so there's 60 questions, I think, available. Ideally, the more practice you do, the better off you'll be as far as the material goes. So I'm going to try and see what I can work out with Sapling to cut the homework assignments down to in that 20 range. That would be my ideal number, 20 to 30 per chapter, and then give you access to all of the other questions, so you still had time to be able to go through and practice stuff. Okay. As it is, I don't know if you remember from the syllabus as well, is Sapling is going to get points adjusted on a sliding scale. Ideally, the average homework score will be about an 85 out of 100 points. So regardless of what's happening on Sapling, I'll adjust points accordingly to make sure that that minimally is satisfied. Okay, so don't stress too much if you don't get all the homework done. Try your best, get through it, and we'll see how it goes from there. Okay? Definitely let me know how long things are taking so I can adjust accordingly. I believe we did end on this slide, right? Last week, so we went through and kind of summarized. And the more you'll see the questions that I'll ask in class are going to be, again, going back to these same ideas. Identify those definitions, nucleophiles, electrophiles, apply them for each functional group. So that when you see an alkene, what you see is not a carbon with two bonds between them, but you see a source of electrons. You've got a nucleophile, you've got a base. How can that now react? Or you look at it from the reverse and say, okay, I had to make that pi bond. How can that pi bond get made? So it's evaluating those big differences in chemistry where we actually see some polarity or changes. Okay? From what I've gathered from most students so far is that you guys are super comfortable with substitution. So we'll whip through this really fast. You've got the general the general outline drawn up there with things color coding for each of the individual pieces. You've got your substrate, which is generally just your carbon chain of wherever your leaving group is attached. You've got the leaving group then attached to that main substrate, main chain. And that's going to be whatever takes the electrons away. So again, with our chemistry, what we're trying to establish is that we're getting a partial negative charge up on our leaving group and a partial positive charge on the carbon where that leaving group is based. The idea being that we're identifying or locating some form of chemistry, and we can start to predict where that came from to determine how to make it, or we could look at what we can then do with that. What can we change to that structure? If we push along the what can we do to change it, we can then look at a nucleophile, and a nucleophile would then come in and share its electrons with that carbon, generating a new bond. Everything breaks, falls apart, and we end up with our product. Okay? A couple notational things. See, told you, 2 people. I was right. A couple notational things before we look at the solvent. You'll notice up at the top that I specified the reagent in this case with an M versus an H. What does that mean? What does M stand for? Periodic table. If you were listening to my 130 lectures, which I know none of you are, you might remember what M is. We're looking at a metal. H stands for hydrogen. Okay. What happens to the nucleophile if we had a metal bound to it? What's the electronegativity of most metals? High or low?
Low.
Low, which means they're giving up our electrons. What happens to the nucleophile if it's bound to a metal? It now has more electrons, so the nucleophile becomes negatively charged. What does that mean about its reactivity?
More reactive.
More reactive. If we switch it to a hydrogen, hydrogen's higher electronegativity than most metals, so we get a stronger bond between the nucleophile and that extra atom. That stronger bond means that the nucleophile is sharing its electrons with something else. What does that do to the reactivity of the nucleophile? If it's sharing its electrons with something other than the electrophile, makes it less nucleophilic because it doesn't have those electrons to share. They're going somewhere else. Okay? Other things to address. If we take a look at the solvent, solvent plays kind of an important role in a lot of reactions. We'll look at it show up here and there. It's really important when it comes to substitution reactions. That's where you're looking at for an SN1 mechanism, it being protic, or an SN2, it's got to be polar aprotic. I'm not going to get into the details of that. Hopefully you guys already know that. We'll see what happens when it comes to tests. So how do I want you to address all reactions? So now that we've got an idea, okay, we know what we started with, we know what we ended with. Okay? So we're going to try and come up with a mechanism to look at what things are occurring. Again, we want to go through and identify the bonds broken and the bonds formed. What bonds were broken? All at once. Good job. Carbon leaving group also broken. We could look at the metal hydrogen nucleophile bond being broken. And then we also have a couple bonds formed. Notice I'm color coding red for broken, blue for formed. So really we've got 4 different things occurring here. When we go through and look at substitution reactions, okay, we actually simplify these terms and we ignore the metal hydride or the metal hydrogen bond and the metal hydrogen bond period, either with the leaving group or with the nucleophile. Why do we typically ignore those bonds breaking or making? How strong of a bond is there between a metal and a nonmetal? What type of bond is there between a metal and a nonmetal? Ionic. If we look at our strength, if we go all the way back to that chart we showed last week, ionic bonds may be a very strong force, but as far as bond strength, one of the weaker bond strengths. We aren't seeing that electron sharing. So why do we ignore that bond? Because it's really easy in any solvent to both make and break. If it's easy to work with, why should we bother to spend our time with it? Okay? So when we look at substitution reactions, there are 2 things occurring. We break one bond and we make one bond. Think back to your mathematics. If we've got 2 possibilities, how many different ways can those 2 possibilities occur? Get 3 opportunities. We could make one, then break the other. We could break one, then make it. Did I say that one already? We can make, then break, then make. And then we can do it all at the same time. Right? So 3 opportunities. How many substitution mechanisms are there? 2. What happened to that 3rd one? Why is it never talked about? That 3rd one is the make, then break. Why do we not evaluate that mechanism? If I make the nucleophile bond first, why is that a problem? How many bonds does that carbon currently have? 5. Why is that a problem? Breaks the octet rule. We can't have 5 bonds. Okay? So when we're evaluating all mechanisms, what we're doing is just looking at the bulk, what things changed across the reaction, and then evaluate all possible circumstances. Once we know all possible circumstances, then we refine. Okay? No one sat down and said, oh, it's an SN1 mechanism, it's an SN2. Okay? They sat down and said, what are all the possibilities? Now I've got an idea of how it occurs. What can I change to the reaction and see how that affects the overall reaction? Okay? So then we get our SN1 mechanisms. You're breaking the carbon leaving group first, then you make the carbon nucleophile bond. So you end up getting multiple steps. Typically, you'll see an extra acid-base step in there. So we get step 1, breaking of the leaving group, our nucleophile coming in, making that bond, and then our leaving group coming and pulling off the hydrogen. Okay, so it's very generically drawn here. What's an important revelation in this mechanism. Which step is the slow step?
Step 1.
Why is the first step the slow step?
Because you're waiting for the leaving group to actually leave.
And the second step, you're waiting for the nucleophile to actually attack. So why is that first step, why is it more difficult for the leaving group to leave? Because I would say in the second step, you got two things that have to come together, right? Two things that have to somehow come together and react. Okay, if you're going to go out and do something with a friend, what's easiest? If you go out and do it by yourself, or you wait for your friend to meet up, which is going to take longer to go through and do. It takes longer to meet up with somebody else. So why is that first step slower than the second step? What's the result of the first step?
Oh, carbocation.
You have a carbocation, also known as a charge. Most charged things are bad. Okay, so if we see a charge structure, that usually takes some effort to try and make that charge structure. So in the case of an SN1 reaction, our first step is the slow step because we end up immediately jumping in higher energy to a charged state. Okay? If we look at the second step, okay, what's happening? We move from charged to charged. Okay, we're unstable in both situations. So there really isn't anything good or bad about that one. If we look at the very last step, we move from charged to neutral. Should that step be fast or slow? Charge is relatively high energy. Neutral is relatively low energy. Is that going to be particularly favorable? So known as an exothermic reaction. Typically favorable. Okay? So our first step is the clutch step when we look at an SN1 reaction. So if we looked at the rate law, our rate is going to be equal to the rate constant times the concentration of the substrate. We do not care about the nucleophile. Why not? Is there a nucleophile in the first step? No. So we don't care about it. Okay? All the other rules that you might remember about these. So what's something else that you remember about an SN1 reaction? Anything? Okay, protic environments. Why do we favor a protic solvent? Way to pick like the hardest one, by the way. But it's fair game. We look at a protic solvent. It's protic because we have a hydrogen bound to an electronegative element like oxygen. Why does that solvent facilitate this reaction? For this reaction to speed up, what do we need to do?
Get the leaving group.
Okay, get the leaving group to leave. Okay, what's going to allow that leaving group to leave? Should it be stable on its own? Yeah, it wants to be stable on its own. The leaving group leaves and it's what charge? Negative. How can we make that more stable? Make it less negative. How do you make something less negative?
Add something positive.
Add some positive. What's special about a protic solvent?
That's hydrogen.
What's special about that hydrogen?
It adds to the
It's partially positive because
Oxygen, so electronegative.
the oxygen is extremely electronegative. The leaving group can be stabilized by our polar protic solvent. Right? What else could we look at? We could look at the cation. For this reaction to work, not only do we have the leaving group leaving, but the cation must also be stable. How can we make that positive charge more stable? What made it unstable to begin with?
Positive charge.
It was positively charged. How do we make something less positive?
Add some negative.
Add some negative. What does a protic solvent bring in? The largest partial negative we can generate. Okay? So that's where our solvent dependence comes in. Anybody else remember anything about them? Say maybe about a substrate. Primary, secondary, tertiary substrates favored. Tertiary, why? pushing a different thing, but yes, let's go back to the substrate. Why is a tertiary substrate better than a primary? Why is it more stable? What makes that structure unstable? It's positively charged. How do we stabilize positive charge? Add a negative. Okay, if we bring in a source from outside, that defeats the purpose. So we've got to look within the structure. So we could look at the electrons around it. Okay, if this was a tertiary substrate, we've got carbons out here, right? What if it was primary? What would those atoms be?
Hydrogen.
What's the difference between these two substrates? Any difference? One looks like it's better drawn than the other, right? What else?
Carbon's more electronegative.
I do kind of wouldn't give that. More electronegative than what?
Then hydrogen.
Hydrogen. So we are comparing it. Our difference is carbon versus hydrogen. So we could look at electronegativity. Okay, you're right. Carbon is more electronegative than hydrogen. By how much? Very little bit. So little that when we bond a carbon to a hydrogen, what type of bond do we have? Covalent, nonpolar covalent, equal sharing of electrons. Okay, so I like the idea. You're thinking along the right lines, but we're going to say there's not much of a difference there. What else is different between carbon and hydrogen? So electronegativity is a good call. What else is different? Two things we're going to keep coming back to again and again and again, every single reaction, broken record. Electronegativity and, yes, size. What's the difference between hydrogen and carbon as far as size? Carbon's bigger. Why does that matter? What makes it bigger? Has more electrons. Why is that important? We're putting more electrons around that positive charge. What does that do to the positive charge? Makes it less positive. Stronger is kind of a weird term to go with on that one. That's why I kind of left that blank.
Counterbalance it, it has to be more positive to counterbalance the more negative.
So the negative will balance out the positive and make the positive less positive, more neutral. The more neutral it is, the more stable it becomes. That means when we go through and do that transition, we start from our neutral and go up to our higher energy state. But now our higher energy state is a little bit lower because it's tertiary. What does that do to the speed of the reaction?
Increases.
It's going to go faster. Okay? You guys remember anything else? Oh, you said something about nucleophiles. Okay, you said weak nucleophiles. Why weak nucleophiles? Fair enough. It's typically how it's taught. I'll try and make you think harder than that. Doesn't mean I'll succeed, but I'll try. Big hint, I did cross that out for a reason at the bottom there. What's the rate of our reaction dependent on? Substrate. So let's make the nucleophile really, really strong. It's an awesome nucleophile. How does that affect the rate? It doesn't. So do we care about the nucleophile? No. As long as we have an electron source, we don't really care where it comes from. So when we're looking at an SN1 reaction, we don't care about the strength of the nucleophile. Okay? Because it doesn't happen, or it happens so fast in a secondary step that we don't have to worry about it. Okay? There are other things you could evaluate. Stereochemistry. If we started with stereochemistry with our starting material, what happens to our product? Thinking along the right lines, but not quite. What did you say? You get both. You get both R and S. Depending on who you talk to, you'll see a little bit more of the inversion, but let's go to the ideal circumstance. In the SN1, typically see both. We get a racemic mixture. Why? We start with stereochemistry at the beginning. We've got a chiral molecule. What does that mean we're going to end with? Probably still have that chiral carbon. Right? Why do we lose stereochemistry in this? What's the result of your first step? First step. How many things are attached to that center carbon?
Is it the FP orbital?
It's the right idea. We have 3 things attached to it. That is 3. Okay, if we have 3 things, do we have a chiral carbon? Typically no. Most cases no. Go back to the p orbital. What is the p orbital going to do for you? Where does a p orbital exist?
You end up in trigonal planar circular pressure on the top of it.
P orbital has empty space, both above and below. Where can the nucleophile come in and attack? It comes in from the top. We end up with one stereocenter. What happens if it comes in from the bottom? You end up with the other stereocenter. The result is, based on our mechanism, we would expect a mixture of both stereocenters because our intermediate, our most important process, our most important step, generates a structure that has no chiral center, which means the rest of the reaction isn't going to be chiral dependent. Okay? So evaluating the mechanism determines a lot of the things that you guys probably already went through and memorized. Okay? What if we move to the SN2 reaction? What happens in the SN2? Now everything happens all at the exact same instant. So tell me some memorization things. What have you guys memorized?
One step.
One step. Good call. There's one step, and we look at the rate. Our rate is going to be dependent on the substrate and the nucleophile. Both reactants in that one step. Go all the way back to 152. Okay. So we could see them both being important. What is that going to do to the importance of our nucleophile? In the SN1, we didn't care about the nucleophile because it wasn't in our slow step. When we move to the SN2, it's now really important. If we make the nucleophile stronger, we would expect the reaction to go faster. We're increasing the overall effectiveness of that concentration. What other things did you guys remember?
Protic.
What was that?
It.
I didn't quite hear you.
A protic. Right?
Okay. I think it's maybe just how you're saying it. Aprotic?
Aprotic.
Okay. No, that's fine. Aprotic solvents. Still needs to be polar. Why does it need to be polar? Do we see any charges floating around in our reaction? Yes. To stabilize those charges and allow them to interact with other things, we have to have a polar solvent. We can't go to completely nonpolar. What about the aprotic? Why do we not push to the extreme protic situation of it? Say a hydrogen and oxygen again. What charge does our nucleophile need to be? Negative. If we have a protic solvent, what do we have a lot of floating around? That positive H. What does that positive H interact with? The negative of the nucleophile. What does that do to the reactivity of the nucleophile? It's now more neutral, less reactive. So we want a solvent that dissolves everything, but then doesn't neutralize the reactivity. Okay? We could go back to primary versus secondary versus tertiary. Which substrate's favored? Primary. Why?
There's nothing to get in the way of the nucleophile.
Also known in the fancy words?
Steric hindrance.
Steric hindrance. There's nothing to get in the way. Hydrogen is relatively small. Our nucleophile comes in. It can blow right by the hydrogen because how many electrons does hydrogen have? Not really any. It kind of depends on how you want to look at it. So if we take our nucleophile with a bunch of electrons and it comes up to hydrogen with virtually no electrons, we don't get that repulsive force. What if we made it a carbon? What did we say was different between carbon and hydrogen? Carbon had more electrons. We get that electron-electron repulsion. Slows the reaction down, prevents the backside attack. If we look at steric hindrance, or sorry, that's not what I was going for. Stereochemistry. Okay, why do we see inversion? Because our nucleophile has to come in from the backside. Why does it come in from the backside and not from where our leaving group is leaving?
Leaving group get in the way.
The leaving group leaves with what? You're absolutely right. What is the leaving group taking with it? Electrons. So that means the leaving group has electrons or a negative charge. What happens when the nucleophile that has electrons gets near it?
Propulsion.
Repels. The nucleophile can't get into the carbon. Okay? So evaluating electronegativity and size determines all of these things that you guys in theory already memorized. Okay? So as a general review, I summarized all the big ones up there. for both the SN1 and the SN2. In theory, you already have this memorized, and we just talked about it, so I'm going to skip over it. If we move to the elimination, what happens in the case of the elimination? It's the exact same chemistry, except this time we get rid of the nucleophile. What do the nucleophiles supply?
Electrons.
Electrons. So if a reaction is still going to occur, what do we need to find within our material? Electrons, okay? So where are those electrons in the case of the elimination? Well, if we've got everything drawn out, it can help us because we can see that we have that carbon-hydrogen bond. The electrons that we use in the elimination come from there. Okay? If we can't find electrons outside the structure, you got to find it within. Okay? We still get an E1 versus an E2 elimination because it comes back to these options. Okay? So the options that are listed out there is just an evaluation of what things had to occur. Do they happen at the same time? Do they happen at alternating times? Which one happens first? Okay? So it's breaking down those basics and generating a mechanism that describes each of those, and then propagating your chemistry further out. Okay? So E1 versus E2 mechanisms. Okay? Again, summarized up here. I decided I didn't want to go through it all. The one thing I might step aside for, Hofmann reactions. Anybody familiar with the term Hofmann? Feel free to volunteer. Okay, let's try it this way. Is anybody not familiar with the term Hofmann elimination? Okay, we had a couple people, so let's take a step back. What's going on with a Hofmann elimination? So let's take a look at I can color, draw, I promise. Put in our chlorine here. And let's go ahead, sorry, I'm going to draw it, shift it over. Hofmann eliminations are a very special case. Okay, they happen in very particular circumstances. They really only happen in an E2 elimination. Anybody remember what kind of base or what kind of material, now that I gave the answer away, that we need for an E2 elimination? Typically, it requires a strong base. Why? When we do an elimination, there's two things that occur. We remove the leaving group, and that's our leaving group. What's the other thing that has to happen? We have to remove a hydrogen from our structure. That means the structure is acting as, if it is losing a hydrogen, it's acting as an acid, which means we need it to react with a base. In an E2 reaction, everything's happening at the same time. We need something to make that bond break faster. So what we can use is a base. Okay, in this case, I picked ethoxide, or the substitution aspect in this case. If we were going to predict the results of this reaction, what might you say? Zaitsev. Everybody familiar with Zaitsevs? Ish. We'll stick with ish. Hope that works. The result is we remove a hydrogen and we remove our leaving group. Right? Which hydrogen do we remove? How many hydrogens are possible to remove? Go to our alpha positions. We got two hydrogens there. How about over here? Are those possible? How about up here?
No, I don't think so. Can you?
Okay. So what's the result? If we pull, man, I should have color-coded. Pull the top one's purple. Purple because Hofmann's favorite color was purple. Don't believe me? Look it up. We end up with two possible products. We can form our double bond on the interior there. If we pull from the other hydrogens, we end up with the exact same products. We won't draw both of those. But what happens if we pull the hydrogens from the top, our purple hydrogens? We still kick off the leaving group. We still remove a hydrogen. Why do we expect one product over the other? Addition was supposed to be your weak point, right? So elimination, you guys have backwards, nail forward, backwards.
Some hydrogen favors.
And then the Hoffman is less stable.
Okay, so it comes back to stability. If we take a look at these two products, what makes each of these products more reactive? Or what makes either of these two products reactive, period? I know, now we're pushing into your weak point. This is addition. Both of these species are reactive because of the pi bond. Which pi bond is more reactive?
The external.
Why? Could be a very simple answer on that one. You provided more information than you needed in the first statement. The external one is more reactive because it's external. It's out on the outside, it's more accessible. So when we're trying to generate a product, do we generate the highest energy or most reactive, or do we generate the lowest energy? Typically aim for the lowest energy. So when we're looking at most elimination reactions, we generate our top structure here, okay, or our orange hydrogens. Okay? That's where we get our Zaitsev's product, okay, which is spelled a million different ways, but I decided to stick with the Z this time. And I think I spelled it wrong anyway. What happens with the bottom one? Well, we would say that one's not predicted, and that's where Hoffman was, you know, the guy that was looked down upon. It turns out that we can force the Hoffman product to occur. What's going to prevent or allow one of these over the other?
I don't know which hydrogen you take on.
Okay, it depends on the hydrogen. How can I make sure that the base that I use removes the purple hydrogens and not the orange ones? Hmm?
Does the size of it?
Has to do with size. It's going to come down to availability. If I make the base really, really big, okay, the classic is tert butoxide, it is now sterically blocked, meaning that that oxygen really cannot get in to our orange hydrogens. And it's going to react with the most accessible hydrogens possible, the ones being out on that primary methyl group. So what ends up happening, we generate with something like T-butoxide, the Hoffman product. There are some limitations to this. You need a bulky base and a tertiary leaving group. If you got those set up, you'll get the Hoffman product predominantly. Okay? You can get the Hoffman product in other circumstances, you just don't get as much. So if you really want the Hoffman product out of this, these are the two circumstances you need. You need that bulky base and your tertiary leaving group. Okay? Which is why if you go back to the slide, see, is that going to go back? Yeah, it does. In the E2 mechanism is where you'll see the Hoffman product. You typically don't see it in the E1 because the thing that really drove the Hoffman product was the bulky base. Okay? The base is the equivalent of our nucleophile. Is it important in our one-type reaction? No. So to get the Hoffman product, we need a strong base that forces us necessarily into the E2 mechanism. Okay? So now into the addition reactions. So looking at your alkenes and alkynes. When you look at these, their chemistry is very, very, very similar. In most circumstances, we'll pick out some of the different ones. Okay? Bottom line, when you look at those two functional groups, there's one thing I want you to see as far as a reaction goes. What should you see?
A source of electrons.
Source of electrons. Those p orbitals are further away from the rest of the structure. They are more reactive. You have a source of electrons when it comes to an alkene or an alkyne, which means your alkenes and alkynes will act as nucleophiles or What's the other species that acts as a source of electrons? A Bronsted base. Okay? So to get them to react, what do we need to react with our alkenes or alkynes? An electrophile or an acid. Okay? So almost all of your addition reagents will follow or fall under these categories. Okay? The next big thing to consider is going to be how does that alkene react. So there's a couple things that we can look at here. I've noticed most teachers don't go into this, but I would push you towards this direction. When you're trying to figure out how something reacts, look at a resonance structure. Doesn't matter if it's good or bad. Typically, the bad ones are actually better for predicting chemistry. So if we take a look at an alkene, we get two possible resonance structures. We're going to take the pi electrons, and we either shift them towards the left, and we get, whoops. Oh, it's a good thing I did it this way. We push our electrons to the right, we get the leftmost structure. If we push our electrons the other direction, we get the rightmost structure. Okay? Why does that matter? What happens if we go through in that box, I make it an R? Which resonance structure is preferred?
There's not going to be a difference.
There's absolutely no difference. Which means when we go through the reaction, both carbons are equally likely to be negative, both carbons are equally likely to be positive, which means we end up with a whole plethora of possible products. Okay? Particularly if those R groups are different from each other. What happens if instead of doing an R group, though, I change it to, any guesses? Let's make it a hydrogen. Now what happens?
The one on the right would be favored, where the electrons end up on the left.
Which do you want to look at, positive charge or negative charge? Okay. If we look at a positive, how do we stabilize positive? We need to give it electrons. So let's go through and take a look at these two cases. Take a look at our leftmost structure. Our negative is on what type of a carbon? We said positive, sorry, my bad. Let's try that again. Our positive is on which type of structure? Primary, secondary, tertiary. If we look at our other one, where is it? Whoops. Primary. Where would we rather have the positive charge, on a secondary carbon or a primary carbon? Secondary, because carbon supplies more electrons to stabilize that carbocation better. So that would suggest that if our box was an H, we would expect the leftmost structure to work out best for us. But there is that negative, so let's switch it up and take a look at the negative. Okay? What happens with our negative? Where is a negative more stable? So if we take a look at our leftmost structure, our negative is at what type of a carbon?
Primary.
And in the other one?
Secondary.
Where would we prefer to have a negative charge? On a primary, why? This one's a little bit more counterintuitive, I think. What makes our carbanion dangerous or reactive? It's negatively charged. How do we stabilize a negative charge? Okay, we could add something to it, but that's again bringing something in from the outside. Okay, and when we're looking at reactions, typically what do we move? Electrons. So we can't add electrons to it, but you suggested another good option. What's the other one? Try and prevent access to electrons. What's the difference between a primary and a secondary? In the primary, there's hydrogens. In the secondary, we've got the carbon. What's the difference between hydrogen and carbon? Carbon is bigger, which means it has more electrons. In the case of the secondary, we are putting more electrons in the same space. Does that make it more reactive or less reactive? more reactive. More electrons in a tiny space, the more reactive it becomes. Okay? Which suggests, looking at the negative charge, that our leftmost structure wins again. Doesn't matter which way you cut it or slice it, we still end up with the leftmost being our more stable one. Okay? Why is that important? Well, in each of your reactions, you are going to add two species to your structure, a positive and a negative. Where that positive and negative go are based pretty much solely on the resonance structures generated here. Okay? The one last thing that we could do as far as a resonance, we could split that homolytically and look at radicals, and I'm going to kind of leave that one alone. Okay? Okay, we'll deal with that when we cross that bridge. When are we done? 55. Okay, good. We're running at a reasonable pace. So the intent was just to throw this up here, be like, boom, here's your alkene addition summary. Perfect. Everybody got it? Good. And we're just going to move on. After talking to a few people, we'll slow it down and come back over a few of these. Okay? So there's some things that you might need to evaluate. Markovnikov versus anti-Markovnikov. There's a big rule that typically pops out with addition reactions. I personally hate having to memorize names. Okay? Believe it or not, I already explained Markovnikov and anti-Markovnikov. How did I do that?
The left was Markovnikov.
Looking at your resonance structures. Okay? Your Markovnikov versus anti-Markovnikov is all about where the hydrogen goes. Okay? If the hydrogen, I don't even know the rules on it, to be all honest. If the hydrogen goes to the least substituted, it's Markovnikov. If the hydrogen goes to the most substituted, it's anti-Markovnikov. Okay? Typically, what charge is a hydrogen? Positive. If we go back to our mechanism, our hydrogen is going to go to whichever one's negative. Okay? Between these two, we said this one was primary, our leftmost structure was primary, and our rightmost structure was? Which one's more substituted? The secondary one, that would be anti-Markovnikov putting the hydrogen there, or Markovnikov putting it where it naturally belongs anyway. Okay? Why I find this even further upsetting is that it really does just push strict memorization with the reagents and understanding zero about the chemistry. Okay? So we'll look at why it's actually irrelevant when we look at the chemistry of a classic anti-Markovnikov reagent. Anybody know? Classic anti-Markovnikov? Let's see, where is it on here? There's one of your classic examples of an anti-Markovnikov addition using boron. Okay? Again, we'll discuss that chemistry in a little bit, okay, on one of the next slides. What we're going to do is still evaluate the double bond responding as an electron source and how it reacts with each of these species. Okay? So let's take a look at alkenes reacting as bases first off. Okay? If we go through and look at each of these reagents, okay, which of these makes you panic the most? Or why do any of these reagents make you panic slightly? Okay? You think panic, think it's getting thrown at you. I'm a real nice person. Okay, so let's make this as HCl. Why do you panic with that reagent being thrown at you?
Halogens usually make strong acids with nitrogen.
So you're saying you're concerned about the halogen?
Well, I'm saying that first reaction, the H they have.
HCl is a strong acid, right? Which part of HCl makes you nervous?
Well, the hydrogen.
The hydrogen ion, that positive charge. So what we're going to do is go through and look at how it reacts with an alkene. So let's look at an example alkene. And I'm going to try and avoid green. I see you guys having trouble seeing that. Let's pick an alkene here. Let's react it with our H+. What happens? What does our alkene act as? An electrophile is looking for electrons. It loves electrons. Electrophiles are typically also what charge? Positive. Is our alkene positive? Our alkene is an electron source. Okay? Our hydrogen lacks electrons. How can we show these two reacting with each other? Starting where?
pi bond.
We'll go from the pi bond to our hydrogen. There are two possible products that we could draw out of this. Sorry, not green. Put our hydrogen here, or we could put our hydrogen on the other side. What am I missing so far in this structure? Or are they both perfect and beautiful? Yes, thank you, charge. We take a look at our starting material. One was neutral, one was positive, which means the charge on our product needs to be positive. It must match the overall charge. Okay, so where's that positive charge? Opposite side of the hydrogen. Put the positive charge here, or in the other case, positive here. Which of these two products is favored? What makes these two products bad temporarily and intermediate and not a final product? They're charged. Okay? Do they have an equal opportunity for existing? Do they have the exact same energy? No. Why not? So you're shaking your head. Why not?
Because the one on the left is more substitution.
So we have a secondary carbocation versus a primary. What does that mean? As soon as we form that primary, it goes, oh crap, I'm unstable, and it falls apart, immediately goes backwards, meaning we don't see that exist for any extended period of time. What's the result? We now have this positive charge floating around. Still bad, we need to fix it. How do we fix it? We could evaluate for rearrangements. Anytime you see a cation, you should think rearrangements being possible. In this case, there's nothing you're going to do to stabilize that secondary carbocation. What do you need to stabilize any positive charge? Rearrangement does the same thing. Electron. Okay? We don't have any electrons within the structure, so where do we need to look? Look for the electrons outside the structure. If this was our first example, what's our electron source? Halogen. The halogen can then come in, form that bond. We now have our addition reaction. Our product is neutral and we're happy. What about the second example? What's our electron source? Don't tell me H2O. The oxygen within H2O. We don't want to look at OH because that means we'd have to pull off a hydrogen, strong base. Why would a strong base be very unlikely to find in any of these reactions? H plus is, sure, we can run, let's just stick with acid. Let's try that first. It's an acid. What's the likelihood we're going to generate a strong base in an acidic solution? Yeah, that's not really a good option. Okay. So mechanistically, we'd have to do something after the fact. What happens in the last case? We still have oxygen as a nucleophile. It can come in and react. Okay. Should we draw the last step of that? I should have drawn these a little bit smaller so I could fit it on there. So in the last two circumstances, we will end with this is a product. Okay, so this is the very last circumstance. What charge should that oxygen be? Started neutral, it shared a pair of electrons, so it's now positive. Does oxygen want to be positive? No. Is this the end of the reaction? No. What has to happen? That oxygen needs to do what? What has to happen to it? Okay, it needs to become neutral, so it needs to get electrons. If we had something bringing electrons from the outside towards it, we exceed its octet, which means we have to look within the structure and find a source of electrons within it. Came up with a good option. We can take the electrons away from hydrogen. Okay, what's the result? Careful. For those electrons to go to the bond, the carbon below it needs to have space for it. That carbon already has a hydrogen attached. We can't make a carbonyl. Okay? Okay, just to be mean. Functional group? What functional group is this? Heard ester. Shout them out. What other functional groups do you know? Oh, that's cheating. Because you were right. It's an ether functional group. You should be familiar with all of the functional groups that we'll be working with. I'm going to try and summarize those, and I will probably test you on that every single week. Okay? Throwing out different functional groups, and then you guys just have to name them so you're familiar with them. Okay? So we've generated an ether. Why is this important? Chemistry that we just evaluated as a review of last semester is chapter 14. You've just generated an ether. That's material we technically haven't yet talked about. Okay? What if we'd done the second reagent instead of with our R group? What would our product have been? Instead of an R, that would be a hydrogen. What functional group do we have then? Alcohol, what chapter? 13. Okay? So a lot of the chemistry that you're seeing in the addition chapter is going to show up again and again and again as we try to make each of these new functional groups. So kind of be aware of that. Okay? So in these cases, what we did is just have that alkene act as a base, share its electrons with the hydrogen, and then evaluate what chemistry followed therefrom or thereafter. Okay? We could also have the alkene act as a nucleophile. And this is where we can potentially see anti-Markovnikov behavior with that first one. Okay? And we're going to see this in lab today too. Okay? BH3, let's see, did I actually put that up there? Yeah, I did. Good. Take a look at BH3, trigonal planar, 3 electron groups, boron's perfectly happy. That hybridization is sp2, which means there is a leftover p orbital. What can you put in an empty orbital? Electrons. So what happens in the case of BH3? Let's see. Nope, don't look at that. Not yet. It's the next one. Our alkene can share its electrons with the boron. Okay? And we end up generating a new species. Okay, in the process of that reaction, what ends up happening is the boron now has too many bonds, so it shuttles a hydrogen back the other direction. Whoops, I don't want to do boron yet. And here's our BH2. Wow, magically the hydrogen ion has gone to a different position. It hasn't gone to a different position. It's not hydrogen. It's hydride. We transferred hydrogen with electrons. Okay? Now this species isn't our final product. We typically don't like boron in organic compounds, so we end up having to hydrolyze that off. And we react that with hydroxide in the presence of peroxide, and we end up with our final product, where magically it appeared. Why did you not draw? the heck? See it on my screen. Let's try it again. We appear to have magically put the oxygen, okay, on a different position. Okay, whereas if we went through and had done this with water and acid, the alcohol would have shown up on the other carbon. Okay, so we've got the anti-Markovnikov result. Not because we're doing Markovnikov versus anti-Markovnikov, because we evaluate the chemistry of the individual groups. Our alkene always acts as an electron donor. How does it donate those electrons into what species? If it donates it to boron, we get an apparent different result of the individual atoms. So evaluate the chemistry of the atoms, not so much memorizing the rules. Does memorizing still work? Yeah, it does. You're just going to have a lot to memorize. Okay? So try and evaluate the chemistry behind each of these, and then reinforce with memorization. Okay, the other big one we've got here is the mercury. Okay, so I drew out the structure of that mercury acetate ion. When we put that into solution, it decomposes because those acetate ions are incredibly good leaving groups. Why would they be a good leaving group? What makes anything a good leaving group? It needs to be more stable. Why is that ion more stable? You've got resonance. The negative charge can be donated in, and we get a resonance structure. Okay? What happens on the other side? What happens to the mercury? It now becomes positively charged. What did we just generate? Our electrophile. That electrophile can then go through and react with our alkene. Okay? Depending on the reagent used, actually, let's go through and have it react with it. Whoops. When it goes through and reacts with the alkene, it shares electrons from our pi bond up to that mercury atom. Can anybody tell me anything special about mercury, particularly in comparison to, say, carbon or oxygen? Nothing? Nothing special about it? What's its electronegativity comparison? Much lower. What else can you tell me? It's a lot bigger. Okay? Mercury is so large and it has that extra lone pair that when it sees that positive charge, all it has to do is tweak the bond angle ever so slightly, and it shifts in, and we end up seeing, instead of that positive charge with the mercury on it, we form the mercuronium ion. Close enough. Okay. That intermediate then reacts with the nucleophile. Our nucleophile in this case is the secondary species, which could be water, or we take one of those hydrogens and make it an R group, and we have, instead of water, we have any alcohol. Okay? Now what happens? That alcohol comes in and reacts. It's going to react in such a way to generate the most stable carbocation. What happens is it comes in, whoops, and attacks here, kicks out the mercury, and we've got our alcohol, or our OH, being added in a Markovnikov type fashion, okay, just as we did before. We'd still have the mercury attached. How do we get rid of that? We reduce that off with sodium borohydride. That reagent will replace the mercury and replace it with a hydrogen. Okay? So the end result is the exact same as if we had just added acid and water, or acid and an alcohol. So why bother to go through with the mercury at all? Right? Mercury is particularly toxic, not a pleasant thing to be exposed to. Why should we deal with mercury when we don't have to? Do we have a carbocation in the case of the mercury? No, there is no carbocation intermediate. Why is that important? If you have a carbocation, you have the opportunity for rearrangements. So in the case where we went back and we had the acid in the presence of water or an alcohol, yes, we get the same result as the mercury addition reaction, except if there's a rearrangement possible. If a rearrangement is possible, it will likely occur, ruining our results. If we do not want the rearrangement, we must use the mercury reaction. Okay, so it's an extra little addendum to that reaction. Questions about that? Okay, alkenes acting as a nucleophile with what I'm classifying as not obvious electrophiles. What's special in each of these cases? Okay, well, at least the first, what the heck's going on? Oh, first three all are involving the same species. We're having our alkene react with Br2. What charge is a bromine in each of these, or in this structure? Neutral. Okay. How does a neutral species react with our nucleophile of an alkene?
So the bond broken, one becomes fulfilled with octahedral, the other one becomes an ion.
So what ends up happening, I don't know why I decided to draw that carbon there, but I did. In this case, that alkene is still a source of electrons. If it gets close enough to an individual bromine, so we align perfectly, the electrons in that pi bond will cause the electrons in the bond between the two bromines to do what? Get scared, run the opposite direction. The result is that we now have a partially positive bromine that can react with our alkene, and then we get a bromide as a leaving group from that species. Okay? And we end up with, again, what we would expect, a positive charge. That hydrogen's out there, right? What can you tell me about bromine? It's a good leaving group. More? We don't want to evaluate its leaving group ability in this case because we added it to it. So having it leave right away kind of defeats the purpose. What else?
Talk about size again.
Size. Why is size important? Bromine has a lot of electrons. What's really close to that a lot of electrons? Positively charged carbon. Okay. That bromine atom, just like the mercury, will lean in a little bit. And we generate this one, I can actually say appropriately, the bromonium ion. That bromonium ion now has some stability, and we'll wait for the next bromide to come in and react. Why does the bromide have to come in and react with this? Does bromine want to be positive? No. Okay, so it's an incredibly good leaving group. Once we give the reaction a little bit of time, the bromide can now come up and permanently stabilize. Okay, and we end up with our final product with our bromines, that is an R group, on opposite sides. Why do they add on opposite sides? Think about it as a ring. Okay, we've got that ring with the bromine, okay, kind of aimed upwards. The other bromine has to come in and react, causing one of those bonds to break. Okay? If that bromine came in from the top, what's it going to see? The other bromine. What do both bromines have a lot of? Electrons, they repel. Where does the other bromine have to come in from? Has to come in from the opposite side, cause that top bond to break, and we end up with our bromines being on opposite sides of that double bond forming. Okay? So you'd have to evaluate some of the chemistry there. What happens in the case with the next two, where we're adding Br2 in the presence of water and Br2 in the presence of an alcohol? Why is that important? What can you tell me about the reactivity of water? Particularly if I go through and draw it like this. What's special about water? What does it have? Lone pair electrons. What's special about electrons? Want to react with something positive. Do we have something positive in our carbon structure? Yeah. We had that same positive that our bromide reacted with. Water can act as the nucleophile instead of the bromide. So we can run the bromine reaction where we add two bromines, or what we do is add another nucleophile. That other nucleophile can outcompete with the bromide, and we end up, instead of adding two bromines, we add a bromine and an OH. So we got an alcohol. That reaction, for those of you that care, would be halohydrin. Halo for halogen, or bromine. Hydrin for the OH from water that we added. Okay? In that third case, instead of adding straight up water, we added an OR group. Again, we changed the chemistry, or we changed the end functional group result. The chemistry stays the same. We still have that oxygen nucleophile. So in each of these cases, what we're trying to do is evaluate the nucleophile, the electrophile, and evaluate at each step the possible reactions that can occur. The very last one's a little bit tricky. Bromine was really large, mercury was very large, so that they could kind of lean in and stabilize that positive charge. If we will go through and take a look at that last reaction with hydrogen, what's the problem? And if we just attempted this, so we did this and we'd end up with this as an intermediate, that hydrogen atom is so small it can't really lean in to stabilize the positive charge. What's the other issue? What's the other product? Good answer, but not the one I was looking for. What's the other product of the reaction that's not shown yet?
Proton?
Is it a proton? So the alkene shares its electrons with one of those hydrogens, right? How many bonds does that hydrogen now have? Too many. So what do we have to do? We have to break a bond. We can either break the one we just made, or we take the electrons that are there and put them onto this hydrogen. What's the other product? Careful. Negative hydrogen. Good answer. You have a hydride. Is hydride something that's particularly stable? No, why not? It's a formal negative located in effectively a point. Okay? Charge is better if it's distributed over a large area. If we put it all in a single point, that's very, very bad. Okay? So that's not a stable reaction. So we have to facilitate this reaction to allow it to occur. To do that, we add a platinum catalyst. Platinum, palladium, you might also see rainy nickel or even nickel show up. All of those are there to help facilitate the transfer of hydrogen into the alkene. Please say I put it in there. Oh, I didn't put it in there. Maybe I did it later. Okay? So the alkene and hydrogen will adsorb to a platinum surface. And once attached to the platinum surface, the platinum will facilitate the transfer of hydrogens. And what we'll end up with, whoops, at the end of that, will be an alkane. Okay, we will have removed the alkene functionality and turned it to just carbon and hydrogen sp3 bonds. Why would we ever do that? What's the reactivity of an alkane versus an alkene? Lower, okay? So typically when we run that reaction, what we're trying to do is end our reaction or prevent any other reactions from occurring. So we'll remove the double bond to prevent that chemistry from being a potential, okay? Typically you don't see that show up a lot, but it can, okay? Okay, radical reviews. What is a radical? I want to try and get through a little bit more. Anybody know what a radical is?
When the bond breaks and each atom gets one.
So that's one way we could look at it. If we took a look at a carbon-carbon bond and we broke that homolytically, we could get two carbon radicals. It's an unpaired electron. It is never assumed or never implied. You must show the radical in any of these radical reactions. Okay? The basics of these that I have seen as far as questions showing up on the ACS test, you need to know what initiation is, propagation, and termination. For an initiation step, it's the formation of the radical. So look at your starting material. Do you see a little dot sitting by itself? If no, you're probably looking at an initiation step. Look to the products. Do you see a radical? If yes, that's an initiation step. Propagation. You start with a radical, but in the next step, you generate another radical. Okay, so that's the propagation. You don't lose the radical. It continues to proliferate. The termination would be?
You don't have a radical.
You don't have a radical anymore. You got rid of it. Okay? If we're going to look at individual reactions, you will see radical reactions show up a lot when it comes to alkanes. Because as we already discussed, when it comes to alkanes, there's no difference in electronegativity between each of those bonds, which means there's no reactivity for an alkane. So we're going to have to initiate it some other way to get that alkane to a point where we can react it. That's where we're going to take advantage of radical chemistry. To do that, the most common method is to add Br2. So instead of it being X, we would have Br2. Okay? Bromine is also not very polar, so we need to initiate it, get it started somehow. To get these radical reactions to start, there's two big triggers. Anybody know those two triggers?
Heat.
Yes, heat's not so good with bromine though. So heat typically requires a different initiator with it. But try again.
Light.
Light is the biggest one you'll see. Light can be used at particularly wavelengths that will actually cause the bromine bond to break. Okay, remember, bromine has no polarity. That bond, if we hit it with the proper amount of light, the electrons are going to jump one to each side. And we get two radicals. Those radicals can then go out and do all sorts of crazy chemistry. Okay? Along the lines with heat, what you'd probably be looking at is another species being added, sometimes shown as RO3H is one that you can see. What we're looking at here is a peroxy acid. This bond between those two oxygens out at the tail end in here is very, very weak. We can cause that to homolytically break with heat, also with light. Again, those electrons split, one to each oxygen, and we generate our radicals. Those radicals can then go through and do the other funky chemistry. Okay? Radicals as far as stability goes. Anybody know what to compare them to? Cations or anions? Really? It's cation. Okay? So what substrate was most or preferable for a cation, primary, secondary, or tertiary? For a cation. Tertiary, what substrate's most favorable for a radical? Tertiary. Okay? So you can treat your radicals the same as you can treat cations. That sets up your chemistry very similarly. Okay? So as far as the reagents, with alkanes, you will see bromine show up a lot with light. You might also see it with a peroxide. If you're trying to react the allylic position, so this is kind of important when it comes to the alkenes. Everybody know what allylic means?
Next to the one over.
Okay. So some people know, some people don't. The allylic position is 1 sigma bond away from a double bond. That carbon is at the allylic position. Right? That changes the chemistry of that position due to resonance. So feel free to make it a carbocation and see if you can stabilize that positive charge. Make it a radical. See if you can stabilize that radical position. You'll find you can through resonance. So you'll see the allylic positions react as well as your alkanes. The other common thing to occur, or the common radical reagent to see, would be the species known as NBS, or N-bromosuccinimide. It is typically used in allylic reactions because if you have a lot of bromine present, particularly around a double bond, what's going to happen? Just looked at it. I know we just went through a lot, but see an addition reaction. The bromine reacts with the double bond, not with the allylic position. Okay? So to prevent that reaction, what we'll do is limit the presence of bromine. If we can limit its presence, we can try and help allow for the allylic reaction instead of the addition reaction. Okay? To do that, we'll use NBS. NBS in the presence of light will decompose and generate bromine in very limited amounts. That limited bromine can then be used to react at the allylic position. Okay? I am going to reference you to your textbook for more details on that. Ideally, I was just trying to summarize a whole bunch of reactions here. How much of this was just brutal review and you're waiting for something interesting to happen?